presented by Caltech.
So it's my pleasure to introduce Sakura. Sakura got her PhD from the University of Cambridge in 2003, after which she was a postdoc in Hamburg for a few years, and then she came to Caltech as a McCone Prize Fellow recipient, and she was here from 2006 to 2009. During her stay here, she continued some of the exciting work she had done previously in string theory, but she also started a new project in collaboration with two of our other postdocs, which is applying a particular approach to string theory known as F theory. They were applying this to trying to do particle physics phenomenology. And this was a very ambitious project because on the one hand you want to confront real data, and on the other hand it involves highly sophisticated techniques from algebraic geometry. So you need a broad range of talents to do that type of work. After leaving Caltech, Sakura has gone to university in London, King's College in London, and she's currently a reader there, which is a tenured position. So it's my pleasure to introduce Sakura, who will talk about string theory in the real world.
Thank you very much, John, for the kind introduction. You missed out on the KITP, which I think we should mention, given that Lars is here. So I spent also a year in between Caltech and London in sunny California. So what John said is correct. I'd like to talk about some connection between string theory and the real world. Every person I've talked to about this title, they've said, "Are you sure? What are you going to say? Sounds crazy. Sounds a tough kind of, talk to follow up on." So not to disappoint you, I will actually start with some real world stuff. So this is not the line for the next iPhone or the next Apple Watch. This is when physicists become groupies and wait at 3 o'clock in the morning in front of a lecture theater to get into something. It was the 4th of July 2012. I'm sorry for the sort of bad resolution, but I was tired too. And so a couple hours later, however, then we got rewarded for all this with these fantastic results by CMS and Atlas of the 5 sigma discovery of 125, 126 GeV Higgs. So with this result in 2012, the question is really in particle physics and more broadly in string theory, what's next? So is it the standard model or not so standard? And as a string theorist, the question is really, what is the relevance of string theory for beyond the standard model physics? So when I came, as John explained, when I came to Caltech, I was in the very safe haven of integrability in the ADS-CFT correspondence, a very sharp problem. We'd like to solve ADS-CFT, understand holography to all orders in lambda and the coupling constant. And so we worked on this for a couple of years, and there were two other prize fellows, Natalia Salina and Joe Marzano, who were topological string theory people or other ADS-CFT people. And at some point, we heard all these exciting things about LHC is going to start, there's going to be data, and we just sat down and said, okay, we need to do something about this. So I think yesterday we heard similar stories that at Caltech, people kind of branch out, do new things. This is what happened to us here too. So we sat down and really worked on this for many years now and actually made enormous progress. So what I'd like to tell you about is what really we can say and what are the questions that are outstanding in this field of connecting string theory and physics beyond the standard model. So the phenomenological input is quite simple. So we'd like to require some very, very basic things of our string theory, right? So they sound extremely sort of mundane to a particle phenomenologist. So for simplicity, we'd start with a SU5, a grand unified theory with n equals 1 supersymmetry. So I will not talk about anything that goes beyond non-supersymmetric theories, etc. I always assume there's some degree of supersymmetry. So we'd like to get 3 generations of matter into 10 representation where we have all these multiplets of the SU3, SU2, U1 standard model gauge group packaged together into the 10 and the 5 bar matter, as well as in the MSSM, the minimal supersymmetric extension of the standard model, there are 2 Higgs multiplets, which in the gut model are packaged into the 5 and 5 bar representation. So that's a very simple spectrum. There should also be couplings, which generate the top and bottom Yukawa couplings, so here with the Higgs up and Higgs down. And in addition, of course, there are some other requirements, such as we'd like to have gut breaking. So these triplet Higgses here need to get lifted, and the gauge group needs to be broken to the standard model gauge group. So this is sort of another additional requirement, and usually in guts, we face a problem that there's proton decay. So if you build a model like this, the proton decays in 2 seconds. There's absolutely no point in doing this. So you need some mechanism to actually prevent this from happening. So this is sort of the list of minimal requirements. And then there are sort of more refined things like what kind of mechanism for SUSY breaking you have, what kind of flavor physics, neutrino physics, etc. So these are things that you then supplement as you go along in the analysis. So keep this in mind. This is where we'd like to go, and then say something about the finer structures that would come out of certain string theory realizations of this. Now, string phenomenology is hard, and people have been doing this for many, many, many years. So what is the difficulty? So there are many noble motivations, right? There are grand schemes like we incorporate gravity and gauge theory into one theoretical framework. It provides UV completion, there's supersymmetry, naturalness, quantum gravity, you name it. Okay, so there are lots of reasons to say string theory really should provide some context for beyond the standard model physics, where we can unify sort of gauge theory aspects with gravity at higher scales. So this is essentially our picture of energy scales here, GeVs. This is around the energy scale where we can sort of test things. This is the LHC, very schematically. And string theory lives around 10 to the 17 orders of magnitude higher up at the Planck scale or the string scale. So what we're trying to do is model something up here and say something about the physics at around the weak scale 100 GeV to a TeV or so. So the standard model is extremely accurate. So what we would like to do is, in fact, whatever we do here should reproduce the accurate physics that we know there. Now, we're a bit more ambitious, right? We don't just want to reproduce it. We also would like to learn about what happens at a nearby scale higher up. Bless you. So are there any special characteristics of theories that come from string theory? So is string theory in some way predictive? So string theory is, as you all know, not a theory that's defined in 4 dimensions. So there's one complication here. It's sort of the consistency of the theory requires it to live in higher dimensions. So our sort of favorite space-time R3,1 will emerge only after compactification. So there's some manifold M, which will always be schematically this colorful object here, which tells us some dimensions are wrapped there, and we go down to R3,1 here via compactification of these extra dimensions. So this seems, at first, this was a real drawback of the theory, and we indeed say, okay, it should be really defined in 4 dimensions, but actually, this is really sort of the main place where we can do model building in string theory. So it's actually a blessing. We can characterize properties of the 4-dimensional physics, meaning what happens down here, in terms of the geometry of these spaces up there. Right? So as I look at different geometric characteristics like invariance, holonomies, singularities, symmetries of this manifold, they will then translate into properties of the 4-dimensional physics, such as the gauge symmetry, matter, Yukawa couplings, global symmetries, gauge and other properties that you wish to engineer. Okay, so the geometry essentially is a model building tool in this context. So the challenge here, however, is there's no uniqueness, right? So there could be lots of different geometries, but in addition, there's this whole landscape of theories. So we have So all these perturbative theories at the boundary here, type 2A, type 2B in 10 dimensions. And then sort of as we go into this green pentagon, there's M theory, it's a non-perturbative version of type 2A, and then there's F theory, which is so type 2B, type 1, non-perturbative completion of these theories. So you don't need to know exactly what these theories are, just the fact that there are lots of different string theories. In addition to each one of these, there's a choice of geometry. So you get a huge number of different compactifications and theories that you can now write down. So traditionally, there have been two approaches to tackle this vastness of the so-called string landscape, namely top-down versus bottom-up. So bottom-up says we start here, we engineer something, our favorite MSSM gut model or whatever, and then we try to engineer it sort of in a local approximation. In some, we don't really write down a full compactification, but we write down sort of a patch of the compactification and then engineer it and then hope that it actually extends further up to a full string theory compactification. So this approach, so let me actually go to the next series, so the bottom-up approach, we engineer semi-realistic or realistic models from a local configuration. The advantage is it's realistic, the disadvantage is no guarantee of a completion, and the really main big problem is lacks any constraining features. You can do what you like, it's too flexible. The top-down approach, right, so oops, you start up here and you try to go down. So you pick your favorite string theory, some space M, you look at the compactification, what happens in the effective four-dimensional theory. The advantage is it's consistent by default from the beginning. You've started with a consistent, globally well-defined space and string theory. The disadvantage is you need to do a case-by-case analysis, right? So you pick a theory on some different space that's nearby, you have no idea what happens in the four-dimensional effective theory. So this is well-defined, but it lacks characterizations of any general features. So this is too rigid. This was too flexible, this is too rigid, so what can we do? So the question is how to improve on this. So what I'd like to propose, and this is sort of really grew out of this work that we did with Natalia and Joe here at Caltech, is really to understand sort of more robust features of string compactifications. So we'd like to sort of, pinpoint certain things that will hold irrespective of which compactification manifold you've picked, right? So something that is more universal, right? So one sort of way to call this is the stress test approach. It's still in search of a name, this approach, right? But it's sort of really extracting robust features which we can then apply in the full landscape of these string vacua and make conclusions about the four-dimensional physics that hold more universally. So I'd like to present sort of two sort of ways that one can ask such questions. One is sort of to introduce an intermediate scale consistency, which is also describable in terms of what's called a Higgs bundle. And that's universal. You can write it down for any of these theories, type 2B, F theory, M theory, and even heterotic. So this is a structure that exists in each one of these theories. So once you understand what kind of four-dimensional physics is induced by this structure, it will tell you something about what type of theories you can actually realize in string theory. And the second thing is sort of understanding more systematical geometric features. And this is something I understand at this moment in F theory, and I'll show you a beautiful mathematics. So if you're a more mathematically oriented person, this will be a very nice math result, but it's actually also a cool physics result at the very end. So from these two things, really the point is, once you understand these general sort of robust features of these compactifications, you actually can then also find some imprints of this on the four-dimensional theories. And at the very end, I will then show you how you, for example, could use this to distinguish against, say, a vanilla model that people would have written down, say, as a particle physicist would, say, a GMSB model, for example. Okay, so let me get to the first point. Let's show it very basically. So in lots of string theories, gauge degrees of freedom arise from deep branes, right? So in fact, they arise from open string sectors. So essentially, you can obtain the Super-Yang-Mills Lagrangians from looking at the low energy limit of open strings. So you go into the point-like limit, and the open strings sweep out this sort of higher dimensional object, these deep branes. and then dynamical objects, and the low energy excitations are exactly super Young-Mills theory. So when you actually look at a compactification, you don't just have a flat stack of d-branes like that, but actually you get d-branes wrapping internal cycles of the manifold, right? So you have this object here, and now wrapping through sort of spheres or other submanifolds in the geometry. So the compactification then says, well, there's a subspace times R3, 1, so R3 times S, that's inside R3, 1 times M. And so the open strings that are confined now onto the subspace actually won't probe the full geometry. They will only probe, sort of given some energy E, they'll just probe length scales E over the tension of the strings. So if you're in a low energy approximation, you'll actually see only sort of the very small fluctuations around this geometry, so you get some approximation to M that these open strings will actually see. So the low energy modes actually localized there, so actually what you get is a gauge theory on the R3, 1 times S. So we're studying here higher dimensional gauge theories on this kind of spaces where S is generically curved, right? So it could be a surface and a complex manifold, or it could be a 3-cycle. So the question is, how do I study generally such higher dimensional gauge theories? And there's been lots of mathematical tools developed for this, going under the name of the Higgs Bundle. There's nothing to do really with the Higgs boson, of course, but sort of named by Hitchin in analogy to really the Higgs effect. So essentially what we're looking at is a system, from a physics point of view, of adjoint valued scalar fields, phi, and a connection A on this subspace S, satisfying supersymmetry conditional BPS equations given in terms of this here. Right, so very simple equations which describe supersymmetric vacuum of this gauge theory in higher dimension on S times R3, 1. So the beauty of this approach is it's universal. You can describe it, first of all, as I started off with d-branes wrapping some cycles. So this is the case of type 2BF theory that Joe, Natalia, and I studied here for this type of theories. But it's also actually originated this type of equations in heterotic, when we want to construct vector bundles for certain Calabi-Yau spaces. And also it's generalizable to M theory on G2 manifolds. It's, I think, something that can be developed even further, I think. So the universality of this approach, that you can always think of these 4-dimensional theories initially to some approximation coming from higher dimensional gauge theory compactified on some curved space down to 4 dimensions. So you're actually looking at this type of Higgs bundle is in fact sort of very beautiful. It's sort of throughout the entire string landscape. So once you have this framework, then you can ask, can I embed MSSM guts into this, and what type of constraints do I get from it? And I'll also discuss this at the end. How does this actually tell us anything about the 4-dimensional physics? The geometric relevance of it is, well, I said that indeed these fluctuations, right, of these open strings see sort of an approximation to the geometry of the cycle embedded into the manifold M. In fact, the way we can think about this adjoint valued scalar field is this vacuum expectation of it, a vacuum expectation value of it encodes the local geometry. So these are fluctuations around the cycle, and so in fact one can use that to then guess and construct the global geometries from it. So this is something that we also started with my friends here, Joe and Natalia, and in fact then learn sort of how to actually generate such compactifications in the context of F theory. So this is sort of one universal approach. The second one is to use geometric constraints. And so this is a little bit more, you have to understand more in detail the different geometries. So lots of things have to be taken care of. N=1 supersymmetry, usually in 4 dimensions, requires these spaces to have special properties, such as they have to be Calabi-Yau, special holonomies, right? So it's Calabi-Yau meaning SUN holonomy, or G2 manifolds. Then there are lots of parameters, namely moduli, corresponding to volumes of cycles or shapes. And so these are massless fields, and we have to lift these in some way, and this is usually done by a mechanism that very much depends on which theory you're looking at. So these things usually are very case-by-case dependent. So one of the challenges here was, can we identify some structures that are just very robust, right? So which really don't care too much about what type of geometry we look at, how we stabilize the moduli. And one very sort of nice example of this is to look at gauge degrees of freedom, how they actually arise from singularities in many examples, and I'll explain this to you in the context of F-theory. So we can actually understand a lot of the structure of the geometry, very abstract, using mathematical algebraic geometric tools, and then arrive at conclusions about the compactified theory in 4 dimensions. So let's talk about F-theory. So stress testing F-theory, what I mean by that is, can we actually say something very general about any class of F-theory compactifications that we can write down? So in the last year, since 2008, well, there's been enormous boost in this field. It's really the most active one in string phenomenology. It started off with Morris and Waffa defining the theory as the non-perturbative completion of the type 2B theory that John and Michael Green pioneered. So it's really like M theory is the non-perturbative version of type 2B. This is, more speaking, something like a non-perturbative completion of type 2A. This is non-perturbative completion of type 2B. The really key insight here is the geometry here is not just any kind of special holonomy space. It actually is an elliptic vibration. So we have a space that's now given in terms of a base and some elliptic curve. So above each point, there's an elliptic curve. In fact, this elliptic curve parameterizes the coupling of this theory. And so, in fact, the parameter tau of this elliptic curve, of this torus, exactly corresponds to the complexified coupling of type 2B. And this curve can actually become singular, right? So you have here a smooth sort of torus, and then sometimes one of the cycles can pinch off. And these type of singularities exactly will correspond to gauge degrees of freedom in the 4-dimensional theory, or to matter or Yukawa couplings. So the key insight here is that all the physics is essentially governed by singularities of elliptic curves, and we can study essentially just the structure of those and then learn about the 4-dimensional theories that can be attained in this class of compactifications. So the name of the game is here, singularities of these elliptic vibrations will give rise to the gauge groups matter Yukawa couplings. So how does this actually work? Now, I said we look sort of to these types of deep brains to actually understand gauge degrees of freedom. Well, in this F-theory context, all of this is packaged into geometry. So you really don't bother about this at all, but you actually just look at the elliptic curves and then at the singularities. And so usually when you see this kind of pinched cycle, what you do as a mathematician, you say, in order to understand what's really going on here, you guys have gone dark. You actually need to do a resolution, right? So what it means is you need to actually smooth the space and find out what is actually the smooth geometry, and then you, for example, find this kind of setup. So these lines here correspond to P1s, or complex projective one spaces, which are essentially two spheres, and they can sort of intersect in this tree-like structure in an affine Lincoln diagram. So I haven't told you at all what this has to do with gauge theories. The way you should think about this is, once you have this little house here, this affine SU5 Lincoln diagram, and you shrink it back down to the singular limit, there could be additional modes wrapping this diagram and give rise to massless modes in the limit where this becomes singular again, right? So there are massive modes, they're like wrapped M2 branes, which wrap these kind of cycles, and then in the limit where I go back to the singular geometry, those become massless, and I can then study the 4-dimensional physics, which, for example, then corresponds to an SU5 gauge group. So geometrically, we resolve these spaces. The smooth fibers are trees of these spheres, and they can intersect exactly in an ADE-type affine Lincoln diagram. So for our purposes, we're interested in SU5. So the SU5 Lincoln diagram here with the affine node is sort of like the dual of the affine Lincoln diagram, right, is shown here. And from the effective field theory point of view, we get all the massless modes of the gauge degrees of freedom by the singular limit. Okay? So matter in this context is obtained by essentially looking at how you generate matter in a D-brane context. So I said D-branes are essentially like endpoints of open strings. So for SU5, there'd be a stack of such branes. And now you can ask how I actually get matter in an SU5 gauge theory, and that's done by looking at intersections of branes in this way. And the way you should think about it is there are additional modes stretching between these two brane stacks. And in the limit, when you actually go to this intersection, those modes become light. Right? So at the intersection point, you actually get an enhancement of the gauge group to a higher rank, for example, from SU5 times U1 to SU6. And this enhancement actually then gives rise to the matter once you look at it from the point of view of the SU5 theory. So in this F-theoretic context, you can do something similar. You could look at sort of a generic singularity that appears with this Pinch torus cycle, and then you can hit it with another singularity, and in fact, the singularity can worsen. And it's as simple as that. So along codimension 2 loci, codimension 2 is because you have to intersect two of these loci where the fibers have become singular. The singularity can worsen and you actually generate matter. So we can, for example, get from SO10, SU6, the 10 and the 5 representation by decomposing just the adjoints of these in terms of the SU5 times U1 gauge group. Okay, so as a mathematician, you ask, okay, so this is singular, I need to resolve it to actually see, right? So this picture needs to get resolved to see what is actually happening there. And indeed, you could sort of write down some geometry for this and actually do the resolution. You will see the following kind of diagram. So this was our SU5 affine Lincoln diagram, and then above certain loci, you get an enhancement, and this is the affine SU6. This is the affine SO10 diagram with certain multiplicities, which I'll explain in a second. So what you see is in the resolved geometry, what you get is some of these nice P1 trees then become slightly larger. So some of these curves of these spheres split and then rearrange in these other diagrams, and that exactly are the loci where you generate matter. Okay, and then you can continue, and there's of course the question of Yukawa couplings. Here you collide three of these matter singularities and get, for example, this type of E6 diagrams. Now, at some point then you will ask yourself, okay, so how do you classify these things, right? So all of these seem to depend very crucially on what happens in the fiber. I haven't talked at all about the base. It's only about what type of singular behavior does this elliptic curve have. So what we actually didn't sort of notice is, well, the classic algebraic geometric result is there's, associated to this Lie algebra G for the gauge group in codimension 1, meaning the fibers corresponding to SU5. Each one of these is characterized exactly by an affine Lincoln diagram of an ADE type group. And it's a classification result by Kodaira and Heron, and that holds for any type of vibration in codimension 1. What is not known, or what was not known, is what happens when you actually include matter. So you actually have loci where the singularity worsens. So say R is a representation of this Lie algebra. Then you can ask, so what is the type of codimension 2 fibers? So this is this type of diagram here, here, and here. And what we've shown is, in fact, they can be sort of equally described in terms of decorated representation graphs, which we'll call box graphs, for the representation R. So for example, let's look at the fundamental of SU5. So the representation graph is shown here. So each one of these is a weight, L1, L2, L3, L4, L5. And what I'm telling you is that this kind of coloring of it corresponds to one way of realizing these fibers in an elliptic vibration. And each one of these diagrams is a distinct, topologically distinct realization thereof. Likewise, over here, this is the diagram, the representation graph, where here I have sort of all the weights of the antisymmetric representation of SU5. And in fact, here you get all these types of different fibers. Now, the interesting thing is that I've connected these with lines, and in fact, you can also study how these are connected with topological transitions, which are also called flock transitions. So these diagrams you can then obtain by studying essentially the structure of certain types of decorations of representation graphs. And what I would like to do, if I have the time, is to briefly explain where this comes from. This is for all the string theorists in the room. So how do I connect elliptic vibrations with such decorations of representation graphs? We first look not at the F theory, but the M theory compactification. So if I look at M theory on a resolved elliptic Calabi-Yau, I get a Calabi-Yau fourfold, I get a three-dimensional n equals 2 gauge theory, and because it's a resolved geometry, it's in the Coulomb branch, right? So I actually have switched on vacuum expectation values of the scalar fields and the vector multiplet, and Higgs the gauge group from G down to the Cartan, U1 to the rank of G. And in fact, the Coulomb branch can be characterized in terms of simply a wild chamber. So this is essentially just the rank of G modulo the wild group. It's a very simple structure. Once I include matter, this was already sort of studied by old papers by Seiberg and Tillergater Morrison, is once you include matter in some representation R with the weight lambda, I get this type of couplings in Lagrangian, phi dot lambda. So in fact, these masses tend to go to 0 as phi dot lambda is 0. So the Coulomb branch then acquires additional walls, which are exactly characterized by phi dot lambda, where lambda is the weight, being band is 0. Put differently, the Coulomb branch phases, the distinct ones, are characterized by definite signs of this product phi dot lambda, so it's either plus or minus. And then I can sort of write down all the possibilities. And in fact, I can characterize them exactly by decorations or sign labelings of each of the weights in the representation, or on the graphically denoted in terms of the representation graph. And so this is the object that we call the box graph. Now, not any coloring will give rise to a consistent such Coulomb branch phase. However, we can systematically study what are the constraints on that and actually get sort of the conditions on this. So the connection is then between Coulomb branch phases, which are these sine phi dot lambda is epsilon, some sign, the box graphs, which are these types of colorings. And in fact, these exactly correspond to the resolved Calabi-Yau fourfold fiber possibilities in codimension 2, right? So this is exactly because we've been in the resolved geometry. Okay, so this is the structure, for example, then for, we start with SO10, Higgs to SU5 times U1, 10 plus 10 bar, or 10 plus 10 minus, and then we get this type of structure. And these connections are then, these flop transitions correspond exactly to representation theoretic actions of the quotient wild group of SO10 over SU5. Okay, so this is just the interlude that we can really systematically study this, and it gives a beautiful classification of all these fibers. And so as a mathematical result, that's already super exciting things. But we can actually continue and look at the case of codimension 3, or include Yukawa couplings, and we get this type of structure where each of these diagrams now corresponds to a fiber which is a 10 and a 5, and all these structures, how they're connected by flops, can be also obtained from this box graph analysis. So far, this is really doing a diagrammatic way of studying elliptic curves, or single elliptic curves. This had also some geometric repercussions where you actually then construct the corresponding elliptic vibrations. And so this has also gone off into the mathematics literature. So let me actually get to the physics. So using this analysis, we can in fact constrain also all the possible U1 symmetry. So I said at the beginning, when we do model building, it's not enough to just look at the matter Yukawas, but we also have to have finer structure. In particular, we can look at U1 symmetries, for example, to protect from proton decay. So what we've done recently is actually supplement this information of what type of codimension 2 fibers are there with the information of what's called rational sections. So these are essentially what in the 4-dimensional physics corresponds to U1 symmetries. So from the mathematics point of view, that gives then a classification of these higher codimension fibers with a non-trivial Mordell-Weil rank. In the physics, it just means we can now write on all the possible U1 symmetries that you can have in an F-theory model. And that's pretty cool, because so far you couldn't have said, could I write down a model with a certain U1 symmetry? Using the structure from the elliptic curve, you can actually completely, systematically, and comprehensively say which ones are there and which ones cannot be realized. So this really then calls for a question, can we now study the phenomenology of this? So let me just briefly remind you why this is of any relevance. These U1 symmetries, so there's proton decay. We want to forbid dimension 4, right? So these type of operators. One way of doing this is by a U1 P minus L symmetry, or R parity. There's dimension 5, which also needs to be suppressed to this degree here, and this can be forbidden by a so-called U1 Peccei-Quinn symmetry. So this, for example, can also be just imposed by saying that the charge, the U1 charge of the up type and down type Higgs don't sum up to 0. Okay, so this is because I'm running out of time, I'm just rushing through this. Last slide, this is sort of now a way to actually say, listen, can I distinguish such F-theory models from other models? So this is something we've done together with Matt Dolan and Joe, but then also now with this sort of general classification of the U1s, we'll revisit this. So the F-theory input is the comprehensive universal characterization of these U1 symmetries. The phenomenological input is we'd like to suppress proton decay. There are additional conditions that come from gut breaking of these models, right? So you actually have to ensure that you lift the triplets. There are anomaly conditions from this. Once you put all this together, this system gives you not your vanilla SU5 model, but actually something that has very interesting characteristics, namely the non-universal gauge genome mass ratios of not the usual 1 to 6, but actually some skewed ratios here. And that's something you can now actually look into and say, can I distinguish, say, a standard minimal GMSB, gauge-mediated SUSY breaking model, against such an F-theory model? And for example, there are certain kinetic invariants that you could look at. For example, this combination here, which essentially measures sort of the mass difference between the two neutralinos, chi 02 and chi 01, which due to this non-universality here actually are very distinct from what you would characteristically get. So you can really do a distinction between standard sort of run-of-the-mill type of models against these type of scenarios that we find in these F-theory models, okay? So this is an example of what type of questions one can ask in F-theory. You know, here the main input was we have constraints on the U1 symmetries. The phenomenological input is proton decay, and then we can actually get certain constraints. Okay, so let me summarize. What I'd like to sort of really stress is for many sort of decades of years, people have done phenomenology from this bottom-up, top-down points of view. Here we'd like to sort of use more universal approach, either using the Higgs bundle description or using sort of general properties of the geometry. And this really means you need to dig into the mathematics, right? So you really need to understand what is the structure of these elliptic vibrations. And that usually goes beyond what mathematicians have actually studied. So you need to come up with your own ideas how you tackle these problems. And interestingly, there, string theory can again help you, right? Like in this Coulomb branch analysis. So this type of questions, I think, really need to be addressed also in other corners. Like the main challenge really is here to understand M theory on G2 manifolds, I think, to really make progress in terms of understanding compact geometries and sort of what type of singularities are there. How can we make these type of universal predictions there? Okay, so thank you very much.